Okay, let's start. Today we plan to finish the transient stability section. This is a very busy slide. We ended last week, but it's just gave you the whole process to prove the equal area criteria, which is a very useful criterion to check transient stability for a single machine infinite biosystem. Later, I will give you an example on how about other system. If other system can be equivalent to a single machine infinite biosystem, this criterion can still work. If you read other textbooks, there'll be different ways to prove this criterion. But here, I want to remind you, sometimes we can go back to the general nonlinear dynamic system or some other more general system or general oscillator. For instance, here we use a pendulum to represent the same single machine infinite biosystem. So based on the differential equation, they are totally equivalent to each other. So for the pendulum system, we know how to define the kinetic energy, which only depend on the speed square, and the potential energy, which only depend on the position. So we can define the kinetic energy and the potential energy, for the single machine infinite biosystem. So the equal area criterion is really talking about any disturbance, if that can generate some kinetic energy, that kinetic energy has to be absorbed completely by increased potential energy, which means the speed can decrease to zero, and then the system will come back to the equilibrium. So this little red area indicate the kinetic energy, the power system gain after this disturbance. And the blue region indicate the same amount of energy, but right now become potential energy, increased after the system pass the new equilibrium. So if those two areas have to be equal, if we ignore any losses. But if the disturbance is bigger, which make, for instance, the area under this PM, which is called accelerating area, become much bigger, and you don't have enough area above the new equilibrium to absorb the kinetic energy, then the system will become unstable. So the criterion try to let you figure out which part is the kinetic energy, which is potential energy, so you can compare. You compare the kinetic energy due to the fault and the largest potential energy you can have after fault is clear. If the later is bigger than the former, so the system will be stable. Otherwise, it will be unstable. So it's very useful criterion to study the stability. You don't have to define for instance, the Lyapunov function. But here, if you add the potential energy and kinetic energy together, so that actually defines the total energy of the system. That is a type of Lyapunov function or energy function. But here we can use this visual illustration to study the stability of the system. So it's very convenient. I also left one question at the end of last lecture. So the entire process of proof assumes the losses are zero. But what if we consider, for example, this damping factor, this damping coefficient? So there will be some loss when the power system is oscillating. So what if this loss is not zero? So can we still apply this equal area criterion? It's still useful, but if the system has damping, has some losses, and we can make a more conservative assumption that the system doesn't have any damping. Okay, so then we use the equal area criterion. So if the system is stable, which means the actual system has to be stable because it has additional damping. So which means when the system has damping, the two area, the decelerating area doesn't have to be equal to the accelerating area. So we can make the decelerating area be somehow smaller than accelerating area. So what it means, after disturbance, then the generator will speed up when it passes the new equilibrium point and reach the maximal point, which is C, and it will come back. And if you calculate the two areas, A1, A2, usually A2 is smaller than A1. Okay, so the gap will be the energy lost due to the damping. Okay, so which means this criterion can still be useful. Definitely, sometimes it's not easy to estimate damping. So at the last slides of this lecture, so we're going to show how the damping can change the energy function and make it more difficult to study the transient stability accurately. But if you want to make a conserved assumption, like no matter how large damping is, we always assume the losses will be zero. Okay, there's always no losses. We can always use equal area criteria. If this one tells system to be stable, your actual system will be stable. But there could be some cases the actual system is stable if its loss is huge. The loss will help you stabilize the system. That can make your assessment be somehow conservative. Let's use the equal area criterion to study a number of disturbances. The simplest disturbance is just to increase the PM as a step function. Okay, so we just suddenly increase the PM original mechanical power, which is PM0 to PM, the new value. And we assume that the system is stable. And we want to figure out the stability limit for PM to increase. So here we can assume when we increase to the new PM and the equilibrium, the system will move from old equilibrium to reach to a new equilibrium and pass the equilibrium until this unstable equilibrium point, which is equal to pi minus the angle at SEP. And if the system can still be stable, it doesn't pass this unstable equilibrium point, it will come back. So which means the A1 has to be equal to A2. And if we start from here, we try to figure out the limit for PM. So that will be the stability limit for the step change on the mechanical power. So we assume A1 is equal to A2, and we plug in the formula. So A1 basically just the integration for the shadow area A1, which is equal to this rectangular area, subtract the area under this sine function, so it will be A1. Similarly, A2 will be the area under the sine functions, subtracting the area, the rectangular area under the new PM. Okay. So you just, this should be easy. You just solve the integral on both sides, do some simplification. You get this nonlinear equation. So we want to solve the maximal angle here, which is unstable equilibrium point. And by using this one, we plug in this maximal angle into this formula, okay? And we'll be able to get the new PM. So at unstable equilibrium point, so PM is equal to PE equals to the value when the angle takes the maximal. Okay, so we can further simplify this equation here, and the only unknown will be a delta max. So which on both sides of on left-hand side equation, but left-hand side is a nonlinear function. You can use maybe a trial and error method, like a Gauss method, or use a Newton-Raphson method to linearize the left-hand side and to involve some iteration. Eventually, you can solve this delta max value. And using that value, so this will be the stability limit. Okay, so which means this is really the maximal change you can make on the mechanical power. Okay, so the new equilibrium point will be basically just pi minus delta max. All right, so this is pretty straightforward of using the equal area criteria. Let me ask this question. So if we take this procedure to figure out this limit, So that's a maximal change on the mechanical power as step function. But if I'm a system operator, I want to change the output of generator and to schedule. Sometimes I solve the economic dispatch problem, and based on that, I can know how much I need to change the PM. So what if the change on the PM is bigger than this limit? What should I do? So for instance, this gave me maybe, for instance, if this is equal to 0.2 per unit, okay, which means if original is 1 per unit, so the generation need to increase by 20%. So that's 0.2 is a stability limit. But based on my economic dispatch, for the optimal operating condition, I want to increase the PM by 0.3. What should I do? Do I have to stop at 0.2 because that is the transient stability limit? Or there's any way I can bypass this limit to make the generator operate stably at the new operating point? Like what if this is my my new operating point? How should I arrive at that point without any transient instability? Any thought? So can we operate the system at that new point or no? We cannot. We can. How should we do? Okay. So here we treat the step change in mechanical power as a disturbance, which means that something happened. It's somehow out of our control. But if we have control on how to change the mechanical power, we may not make that be a disturbance. Okay. So what can we do is, let's see, if we want to achieve, this is the stability limit, right? Because we want to achieve this one. If we do a one-step change, this is a accelerating area, but decelerating area is too small, right? System will be unstable. So you can imagine the system will just pass the unstable equilibrium point. But one thing you can do is you don't increase the mechanical power by one step. Instead, you do many small steps. Like for instance, I start from here. At first, I increase to this value. So this will be accelerating area, and this will be the decelerating area. And the system will come back, right, to this point. That's step number one. And step number two, I increase here. So it will eventually stop at there. And step number three, step number four, eventually you can move up to any point if you take a very small step. Yeah, that small step tell how much oscillation you're going to have. You don't want the oscillation to be too large to exceed the stability limit. You only want to make the operating point to be moving slowly to limit the amplitude of oscillation. Then system can still be stable. So basically, you slowly move the operating point up. So eventually, that's the maximal mechanical power you can output. That's why this value is called a steady state limit, which means if you can make the system undergo a number of different small equilibrium point or maybe steady state condition, slowly moving from the beginning to the end, you maintain the system operate as some like steady state or quasi steady state condition. Eventually, you can reach this point. That's the maximal mechanical power you can output. Okay. Yeah, you can get to here, but condition you have to move at smaller step, not a large step. The large step will create some large accelerating area, and you need to have enough decelerating area to balance, compensate that one. Okay, and when you take a very small step, accelerating area will be very small. You only need a little decelerating area to slow down, and it will eventually move up to that limit. So let's talk about the three-phase fault. So we borrow one example from a Kunder's book, and we assume generator is connected to a step-up transformer, then deliver energy to a power to a infinity bus or large system through two transmission paths. And the second transmission path will have a fault on the middle point of the line to the ground. So a right-hand side on the right-hand side will be the equivalent circuit we can use. So the electric power still depend on this formula. So for this case, the E prime is the EMF of the generator, and EB is the infinity bus voltage, and ST is the total reactance of the entire transmission path. All right, so we can draw the power angle curve for this case, but the system, it will have some disturbance and will some protection. The system may have a different electric power output depending on the topology of the system. For instance, if both circuits are in service, so there's no fault, so that will be this function. So but if you have one path, the second path after fault is open. So with circuit 2 out of service, so that will be this function. Because when you open one path, so the ST will increase. Right, so the electric power will decrease. If we also consider the topology during the fault, the during fault, which means how much electric power the generator can still deliver during the fault, when the fault, the short circuit is there. So that really depends on the resistance from the generator to the ground. So if the resistance from generator to ground is 0, a generator cannot deliver any IT power to the ground outside. So which means, so this electric power will be much smaller than the previous two. And if the fault is exactly at the terminal of generator, and there's no resistance between the generator and the ground on the fault location, so the generator cannot deliver any electric power outside to the network. So that will make PE be 0. So that corresponds to this condition. So the PE during the fault will be exactly 0. But for more general cases, like the fault is at this point, so the generator can still deliver a little bit power to the network. So that PE will not be 0. So here we want to use this example to study the accelerating and decelerating areas, and use the equal area criterion to judge the transient stability. So first, we need to ask those 3 questions. We consider a general fault, a permanent fault cleared by tripping the fault circuit, and a temporary fault without losing any circuit, because we don't know what's going to happen. So for a general fault, we want to compare the PE during the fault versus the PE post the fault. Okay. And for the permanent fault cleared by tripping the fault circuit, we want to compare the post fault and the pre-fault for the values of PE. And lastly, for the temporary fault, we want to compare for the temporary fault, which means we're not going to lose any circuit. So the topology of the system after fault is clear exactly the same as the system without the fault. We want to compare the electric power for the post-fault condition and the pre-fault condition. Okay, for the first one. So for general fault, the during fault electric power usually has to be much smaller than the post-fault electric power. Because the fault will limit how much electric power the generator can deliver outside. If it cannot deliver that electric power, if that amount is 0, the mechanical power will totally become the power to speed up the generator. Okay. So when we clear the fault, we want to increase the electric power. Then we can slow down the acceleration of the rotor. So this one has to be true, which means the post-fault condition has to be much better than during fault condition. For permanent fault, if it's permanent fault, the post-fault condition has to be different from the pre-fault condition. So if you're going to lose a circuit, this one, and the post-fault PE will be smaller than pre-fault PE. So that fault, after it's clear, it will reduce how much electric power you can deliver to the network. So lastly, for the temporary fault, without losing any circuit, the electric power before and after the fault will be exactly the same. It doesn't change anything. Okay, so keep those in mind. We can know how to identify the accelerating area and decelerating area, because accelerating area can be maybe somewhere here and decelerating area will be above. But we will have to figure out the area between which PEs, because there are 3 PEs, right? Okay, so this represents a stable condition. So there's a 3 PEs, pre-fault, post-fault, and during fault. When we start from this equilibrium point at A, we start at 0. And when the fault happens, it will move to this point B. That is on the during fault P. And then when the fault is clear, it will move up from C to D to the post-fault P. Okay, so we'll continue increase until point E. And to make the A1 equals A2, then it will come back. So this system will be stable. So if we draw how the angle is accelerated, so it will start from an initial value and after the fault happens, so it will speed up, right? Until it reach the maximal angle. At that point, the speed will go back to the signal speed. It will come back, and then it will oscillate around the new equilibrium point. New equilibrium point is actually here is. So this will be new equilibrium point. So finally, it will oscillate around the new equilibrium point. So this will be the stable condition. Another condition will be unstable condition. We make the fault clear later. So it take a longer time to be clear. And it will give us a bigger area to accelerate a generator. And then the area above the new PM until the unstable equilibrium point will become smaller than the accelerating area. And the system will become unstable. All right. So the key is to identify which PE you need to use to calculate the accelerating area or decelerating area. So make sure during the fault you use the during fault PE, and after fault you use post fault PE. Next, we want to talk about 2 concepts. First is critical clearing angle and critical clearing time. From previous example, we know if we have wait until the angle increase to a bigger value to clear the fault, and that actually reduce the decelerating area. So there must be a maximal angle by which you have to clear the fault. So that angle is called the critical clearing angle, or CCA. But because in reality, it's not easy to measure the rotor angle in real time. It's easier to just to count the total time take to reach to that angle. Okay, so we use a critical clearing time. So for each generator, we can study the local critical clearing time, like this generator against the rest of system using some like single machine infinity bar system model. And we can use this critical clearing time as some threshold for local protection. So the protection time need to be shorter than this critical clearing time to make sure the generator is stable under disturbance. So here we assume a similar case. The during PE is just 0. So this is during PE. During fault PE is just 0. Okay. Because we assume the fault is just directly at one terminal of the generator. So we study this critical condition to make A1 be equal to A2. Then we try to solve. Our goal is to solve this angle, and then we solve how much time to take to increase from initial angle to this critical angle. So we plug in on both the formulas on A1 and A2, and then you can solve the critical angle has to satisfy this nonlinear equation. If you solve, and definitely you only just calculate the R cosine, this expression that will give you the critical angle. The next, we can solve a critical clearing time. Because here we assume that the PE during the fault is 0, which means the swing equation on the place we have PE, we can replace that one by 0. Okay, so this will be the angle being accelerated completely by the mechanical power. So all the mechanical power is used to accelerate this angle. So if you integrate both sides, left-hand side will become a first-order derivative of angle, and right-hand side, if you do the integration, is basically just integration of time. So we'll give you this one. So which means the speed increase as a linear function of time. So when the fault is there, the short circuit connecting the terminal of generator to the ground directly, before the fault is clear, the speed increase as linear function of time, linearly with time. So you can imagine the speed can increase quickly. So if you start from 60 Hertz, even after a very short amount of time, the frequency can become very bad, right? It can damage the generator. And if you further integrate both sides of the equation, so you can get a quadratic function of time for the angle. Okay, so critical clearing time will be basically just you plug in the critical angle on the left-hand side, and then right-hand side, it will be the critical clearing time. So you use this formula first, solve a delta C, and plug in this formula, you will calculate a TC. From this example, we know during the fault, the rotor angle can increase linearly, and angle speed can grow. Yeah, maybe. Yeah, there's some typo. It should be rotor speed will increase linearly, and rotor angle increase quadratically. Okay, just give you some number to give you just give you some idea about how quickly it can increase. So let's assume this is per unit, 1 per unit, and this point is 2 per unit. So PM is 1. P maximum is 2. And if I assume inertia is 10 seconds, inertia a constant 10 seconds, and this angle is 30 degrees. Okay, so and the delta C will be about 80 degrees. And TC, if you plug in all the value, it's only 0.3 seconds. And when at the time the fault is clear, because the speed increases as linear function, so the frequency when the fault is clear has been about 161 Hertz. Okay, so that can be very bad, right? So that will either trigger some protection of the generator or damage the generator. So usually the protection time is less than maybe 6 cycle, 5 cycle for transmission system. 6 cycle is about 0.1 second. Okay, it's only a third of this example. Let's talk about the more general case. Here we assume the electric power during the fault is positive, is not zero. We know we're going to consider the 3 different P's. So we have the largest one, which will be the pre-fault P, and the next one will be the post-fault P, and the smallest one will be a during fault P. And we know during the when we calculate the accelerating area, we need to calculate this A1, which is the area above the during fault P, but under the new mechanical power. For decelerating area, we need to calculate the A2. A2 is the area above P, the new mechanical power, but under the post-fault electric power. Okay. And here we know the new equilibrium point will be the post-fault P intersecting with the PM. And pi minus that angle will be the maximal angle, which is unstable equilibrium point angle. So here we consider a critical condition. So when the fault is clear at the critical clearing angle, which means A1 is equal to A2. If we just plug in the expression for each A, so for A1, we need to utilize the P. This is just integration of the P during the fault. And for A2, we need to utilize the P for integration during a post fault. So if you do the integration and solve the critical clearing angle, so you'll have this formula. It's pretty similar to the critical clearing angle we proved in the previous slides, but it will be more general because we need to consider both during fault and post-fault P values. Okay, let's discuss about the meaning for those areas, because you may notice also name this area as A3. So A1 here is very clear. That is the kinetic energy you can have when the fault is clear. Because the PM is higher than electric power, so the difference will accelerate the rotor. But what is the A1 plus A3? So that is the area, right? So that means the total energy the generator has when the fault is clear, when the generator moves to a point E. Let's see what happened when the fault is clear. So the generator moved from A to B, right? Then to C. C is here. Then to E. Yeah. This area. So if I draw the path, let me use different color. So we'll go through this process. So when it goes from A to B to C and to D and to C, so that will finish the area A1. So that is accelerated. Then when the fault is cleared, it jumps from C to E. Because the A3 is above mechanical power. Any area above mechanical power is considered potential energy. So when the fault is clear, the rotor has all the kinetic energy again it has during the fault, and also it suddenly gets a new potential energy due to the fault is clear. Because why? Because you change the network topology. The zero potential energy has changed because the equilibrium point has changed. So suddenly gain a new potential energy. It's just like when the ball is moving on the surface, right? It has some kinetic energy, but suddenly you have an earthquake. And for instance, you're standing on this sixth floor, and after earthquake, it suddenly just dropped to a fifth floor, or maybe you just move up to seventh floor if there's a such level. So your potential energy is also changed. So A3 is actually the potential energy increase due to this network change. But you notice that's actually not important at all in our original criteria. So why? Let's explain why that A3 is not important. Then what is A2 plus A3? A2 plus A3 is the total potential energy the system can have relative to the new equilibrium point after the fault. So A2 plus A3 is the maximal potential energy relative to the new equilibrium point. Then if we compare those two, based on the equal area criteria, because remember that the original description about equal area criteria is the energy the system gained during the fault has to be less than the maximal potential energy the system can have. Okay, after the fault, right? So based on original definition, we really need to compare A1 plus A3 versus A2 plus A3. That's the original definition of equal area criteria. If you want to go back to the very beginning, how we talk about, right? So this is actually maximal potential energy we can have. But because this case is very simple, it doesn't change any network topology. But when you change the network topology, you need to find out the total area above the PM, the new PM. So that gives you the maximum potential energy. Then compare to the energy you can gain during the fault. Okay. For this simple case, the energy gained during the fault is only kinetic. But for more general case, that can be both kinetic energy and potential energy. So that's this general case we're talking about. But when you compare those two, the A3 is canceled. So we don't really need to worry about A3, okay? So we still only compare A1 versus A2 here. All right. So this just gives you some clarification. Don't worry about this part, it's not important. Okay, let's discuss further about the shape of the energy. So we know the potential energy, kinetic energies, and potential energy is defined by those two formulas. And if we try to draw this curve, just indicate how potential energy change with angle. Just give you some more visual idea on how the ball is moving along the surface. So this function is actually the potential energy, so which is drawn based on this function. If you solve this function, that will give you that nonlinear curve. Okay. And this bottom point indicate the new equilibrium point. And this maximal point indicate this unstable equilibrium point. But if you continue drawing the curve to the left, eventually you will get another maximal potential energy, and which is this angle. So my question is, what is this one? Why is that different from the potential energy calculated at the UEP? So if we give this angle some value, like for example, this is 30 degree, and this one will be 150 degree. So this is 30 degree, and this angle will be 150 degree. So what is that angle? That angle will be a 150 degree minus 360 degree. So will be negative 210 degree, right? So which means if you draw this potential energy to the left, you'll be able to see another maximal potential energy at angle about negative 210 degree. So if the rotor, when it swing back, it can really reach to that point. That's another limit. But why do we not use that limit? Because the first limit is closer. This 150 degrees closer to the stable equilibrium point. So if it's lower than this energy, it will be definitely lower than that energy. But what does that one mean? That means, let me make it clean something. Okay, so so when the system has a fault, right, it will move following this process and reach to the unstable equilibrium point. And if the system is stable, it will move back. It will swing back. So that the second potential energy is actually the area, this area. So if you integrate the area above PM under the post-fault electric power, so this area is actually the potential energy, the first one. But if you integrate the area under the PM above the post-fault PE, so this will be the second potential energy, the critical potential energy. So that's why it's bigger, but that's not a concern to us, because if the system is stable, it will never swing back to reach that point. There's another unstable equilibrium point. Maybe you can understand that one by this case, right? So this is like, if this is 30 degree, this is 150 degree, and this is so this here, there's another potential energy to the left. But because the right one is closer to the stable equilibrium point, we only just check the energy at this unstable equilibrium point, not the other one. The other one will have higher energy. So if it's stable, it won't get to the further one. Okay. Any question? All right, let's move on. So let's summarize some factors that can affect the transient stability of a generator. Basically, all the conclusions are from this equal area criterion and also the single machine feedback system model. But definitely those conclusions are also useful to any general power system. So the first factor is how heavily the generator is loaded. So that really depend on PM, right, or PE, because PM minus PE. But basically, if we're talking about equilibrium point, that basically is PM. So if PM is higher, that actually make the maximal potential energy you can have above PM be smaller. So definitely heavily loaded generator will have worse transient stability. And the second is the fault clearing time. Fault clearing time will determine how much the angle at the clearing time. So if that clearing time is longer, so delta C will be longer. So that will make A1 be bigger. So if this is increased, A1 will increase. So it will become harder to have the equal A2 to compensate the acceleration. The next one is the post-fault transmission system readiness. So that is this one. So if this readiness is bigger, which means the P is smaller, right? So if you're able to change the post-fault, change the post-fault readiness, that can influence the PE. If PE becomes smaller, A2 will become smaller. So the decelerating area will decrease. The next one is the generator readiness. Lower readiness increase peak power and reduce the initial rod angle. That one also can contribute to ST. Okay, that's similar to the transmission, the total readiness. The generator output during the fault. This depends on the fault location and the type. If the fault is on the terminal, the generator output during the fault can be 0. If the fault is far from the generator, it still the PE will be non-zero. Okay, so that can make a PE be maybe 0 to someone non-zero value, to some positive value. The generator inertia. The higher the inertia, the slower the rate of change in angle. Because based on our calculation for the critical clearing angle, the inertia, if inertia increased, the critical clearing time will increase. A bigger critical clearing time means you have more room to do the control to prevent the transient instability. So lastly, this one, the generator internal voltage magnitude E prime. This one can be controlled by field excitation. So if you can design some controller based on the exciter, the exciter will detect the fault. If the fault happens, that will increase the field current and also increase the E prime. So that will make the PE be increased during the fault or post-fault. So that actually gave you a bigger decelerating area, right? So that will improve the stability. The last one is the voltage magnitude of the bus receiving power from the generator. So definitely this one is also, if you have some controller, if you can improve this EB, that also increase the decelerating area. Okay, so if we color those factors in green or red, depending on whether they are doing a positive, they have positive role or negative role on the transient stability, will be like this one. So first of all, if you increase that value, the system will be more unstable, but next part will be more stable. Okay, just think about those. I went through those items very quickly, but just think about why they can play a positive and negative roles, and even those factors conclusion from single machine infinity bus system, but they're also useful for any power system. All right, so next, I want to mention this one because you're going to use this conclusion for a homework problem, and also we can borrow this conclusion to derive more general equal area criteria. I'm going to talk about in a few minutes. So what if I have a 2 generator connected through a transmission path? So please note, so both generators could be just typical generator. So none of them, neither one is like an infinite generator. So the generator 1 has H1, generator 2 has H2. So how can we apply equal area criterion to this 2 machine power system? First, I can write down the swing equation for each generator, and I do the subtraction. I define the angle difference, which is generator angle 1 subtract angle 2. And then next one, I just do some simplification. I get this formula. So the right one will be the equivalent inertia. And the blue one will be the equivalent mechanical power. And this pink one will be equivalent electric power. Once you get to this model, from now you can just study the system as exactly a single machine infinity bus system. So let's give some typical value for the system. So we just change the ratio of the second inertia to the first inertia. If that ratio is infinite, which is exactly like infinity bus system, So the equivalent inertia will be H1, right? Because the second will become infinite. And the equivalent PM will be simply just PM of the first one. P will be the P of the first one. But in reality, if that's not infinite, only just 10 times, but you still can see it pretty much close to the first generator connected to a large system. When the two inertias are same, the equivalent inertia is only half of the first one. And the mechanical power is half of the difference, and same for the electric power. So this gives you a very useful way to simplify two machine system or two area system to make it be some equivalent single machine infinite box system. Then you can apply the equal area criterion. Okay, so next I'm going to talk about some the direct measures for general power system. There are two types of measures. Most of measures fall into those two types, but there could be some other. But those two will be have been very useful and utilized by commercial software. The first one is the single machine infinite box system equivalent based direct measure, and some reference call it extended equal area criterion. Some reference call it single machine equivalent based direct measure. Okay, but they can both basically based on the same idea for multi-machine system. So the procedure for such measures will be first, according to rotate angle curves, you can simulate over maybe a time window. You don't have to finish the simulation until system really is clear to be stable and unstable. You only just need to simulate maybe for short time window, slightly longer for duration time. Then based on the simulation result, you can partition all the generator into two groups. You call the accelerating group as critical machines and the remaining generators as maybe non-critical machines. Basically, it's just two-way partitioning. Although if you have M generator, based on the combination, there are many ways to partition the generator into two groups, but eventually you only just need to investigate M minus one. So if those are the generators, so first partition is you separate the first one versus the remaining, and the second is separate the first two versus the remaining, right? So for this case, you only just the n equals m equals 5, but the partition is you only need to investigate 4. If all the 4 are stable, the system will be stable. If any one of those 4 partitioning indicate the system to be unstable, system will be unstable. Okay, you don't have to check, like for instance, what I put those 2 in one group and the other 3. You can, if you want, you can also check that partitioning, but you don't have to. You only investigate n minus 1, which will be enough. So for each partition, you can construct a 2 machine equivalent, similar to the one slide, before this slide, right? Then you can have the equivalent single machine infinite box system, and you can use equal area criteria. So it's still based on the same swing equation here. So if you compare to this formula we proved in the previous slide, so we just generalized this formula to many machines. So this formula is just about 2 generators, but here we have many generators. So we have 2 groups. So we have first we calculate the total inertia. So here M is just 2H. So MC will be the total inertia for the group 1, critical group, and Mn will be total inertia of the non-critical group, the second group. Okay, by using this formula, that's the same as this one, right? So we'll have the total equivalent inertia. And next one, we we just generalize this formula for PM and this formula for PE. We'll have the more generalized version for PM and PE. And last one, we need to focus on the angle separation between the two areas. So we calculate the average angle of the first group and the average angle of the second group. So which is like a weighted sum based on the inertia of different generators. Okay, so this is how it's pretty straightforward. That's some method anybody can think of. So let's see the result. So now if there's a 3 generator, this is study for a 3 generator system. And the top 2 generator have bigger angle, and we just treat the top 2 as critical group and the last one as a non-critical group. And then doing the equivalence between the 2 groups, and it will give you this angle curve. So this will be the angle. And using this angle curve, I can calculate to visualize on the pole angle curve. So we will have accelerating area and decelerating area. So this one shows a case when the system becomes unstable. So which indicate the accelerating area is bigger than the decelerating area. Then the system will be unstable. Okay, so using this method, I don't have to finish the simulation. I only just need to simulate maybe until I basically can determine the decelerating area is not enough. Then I can stop there. So if that can be become evident after maybe a few cycles, I can just stop there. I can judge stability. In the last reference, there are some other bigger system examples. For instance, those applications on the hydroquebec system, a larger system, for stable and unstable scenario. So when the system is stable, definitely you see the swing is become more fuzzy. But if you track the one swing, you still can somehow estimate the decelerating area and the accelerating area. So those area has to be equal if the system is stable. Maybe I shouldn't say have to be equal. It's just roughly equal. So A2, you need to have enough decelerating area to compensate the accelerating area. But for unstable case, you see one generator flying away. So if you track the most recent swing, so there's A2, right? And A1 can be smaller than A2. That's why the system becomes unstable. Okay, so this is the one type of derived measures based on the equal area criterion. But if you want to study more general system, we still want to find the transient energy function and to give us a better assessment of the transient stability. So let's use just one slide to talk about the transient energy function method. So I introduced the basic idea in the first lecture of the transient stability, but here let's give us a complete procedure for transient energy function method. This is a multi-machine system model, each generator, which has each generator model in the classical model. So here we just assume no damping, and all the load will be an impedance load, such as we can reduce the network, only keep the admittance matrix connecting the EMFs of all generators. So all the load or network has been part of those admittance matrix elements. So the idea to find out the transient energy function is, so when the system is subjected to a fault, and some of generator, actually most of generator may be accelerated, but some will be accelerated more, some will be less, and depend on the a new equilibrium point, and we can estimate how much potential energy the system will have. But the situation is very complex. But we can take this idea by finding the center of inertia, which is like you have a cluster of particles moving around, but the entire cluster may flying together, right, at a certain speed. But the transient stability is try to make sure every particle stay in the same group. So there's none particle flying away from the rest of the system. So similarly to the generators, we want all the generators stay together, even they together speed up or slow down, but that doesn't change the transient stability. So what we really care is the relative motion to some center of this group. We call it center of inertia. We only just study the motion of those particles relative to the center. So the center of angle is just calculate the weighted average of all rotor angle. So we just multiply each angle by its inertia and divide it by the total inertia of the system. So that will give us the center of the angle. So which is like if the system is a particle and they together just move, right? So the center also move, but we only just care about each particle relative to the center. If that one can be bounded, the system will be stable. So this is the center. Then you just calculate the derivative of this center. It will give you the center speed. The next one, you can calculate the net power the center is introducing. Okay, you basically just add total mechanical power and total electric power for the entire system. So this one has to be utilized to accelerate the center of inertia. So this line just try to treat the entire system as just a single generator. So delta COI will be that angle, omega will be that speed, and this PCOI will be the net power, net accelerating power of that equivalent generator. So next one, we consider motion of each generator relative to the center. So we define theta I, which is the delta I minus the center, and omega I will be just the derivative of theta I. Okay. All right. So the swing equation will become this equation, and we can easily prove. So if we multiply each relative angle by the inertia, and we calculate total, it has to be 0. So next one, we want to, okay, so right now you see this part is like a single machine in feedback system swing equation. And this one indicates the coupling part. It just couple this machine to the rest of the system. So if this one is 0, I can define the energy function, which is the kinetic energy plus potential energy for that part. That's the same as single machine feedback system. I just summate all the energy of all machines together. That gave me a total energy function. But right now, I really don't know whether this one will make some difference. Okay, but so we need to study when we calculate the energy. When we integrate any accelerating power over certain angle, and we want to make sure how this one change the energy. So only this part will will be related to the total energy of the system, and integration of this part can be split into a different generators. If you try to plug in the definition of the theta I, and then until this step, you can prove this one has to be 0. So when we do the integration, and to find out the energy. And the last part that indicates the coupling of all the generator doesn't contribute energy, so which is good. So next step, we just need to define the total energy based on the total kinetic energy and potential energy of each generator. So the energy function defined to be summation of the sum of all kinetic energy for M generators. And then this part will be the integration, which is similar to the area between the electric power and the mechanical power over a certain angle, okay, which is similar to the somehow like decelerating area. And the first item is more like an accelerating area. So this is somehow like A1, this is somehow like A2, but this is for the entire system. We know the PE for each one satisfy this formula. So if you plug in PE, if you do some integration, and you will get to this result. So the first item is unchanged. It's just do the sum of the total all the kinetic energy, and this part is because of the integration of mechanical power, because we integrate from any equilibrium point to any angle. So that can be the angle after fault is clear. And this item is from the integration of the electric power, but contributed by the first item. And this item is contributed by that one. And the last part is 0. So we don't have to worry about that one. Okay, next we just want to figure out the physical meaning of each item. The first one basically just the total kinetic energies. If we count the kinetic energy of each individual generator, right? The sum will be the total kinetic energy. And the second is very clear. That's only an angle dependent. So that's which is potential energy. It's a sum of all the potential energy. The third one is some new item. But that one also only depends on angle, right? It doesn't depend on any the trajectory of the system or the speed of the generator. So it also can be considered as part of energy. The last item will be interesting. Before we explain what that is, we compare, if we calculate the total of those two items, which corresponding to the first item and the second item for single machine feedback system. So far we can fully explain item 1, 2, 3, because those will give us the total kinetic energy and total potential energy when we simply just integrate, add all the energy for each individual generator together. But this item will be something new. And unfortunately, this one is not, rigorous speaking, is not the potential energy. Okay, although it seems to be only depend on theta, but this theta is theta I minus theta j. But I'm going to integrate for theta I plus theta j. So you cannot solve this integral analytically. Which means this is not potential energy, this is something new. But in order to solve that one, you really have to simulate the system until the angle, okay, by which you want to calculate the energy. Then based on the, okay, so you have to do the simulation. This is theta I and the theta j. So at each step, you calculate the difference. So this one gives you theta ij, right? Theta I minus theta j. And you also need to, at each step, you also need to calculate theta I plus theta j. And calculate how that one is going to change. Then you integrate this one step by step. Then you can get accurate value for this last atom. So if you do that, there's no point to use direct method, because direct method means I don't need to simulate. I don't need any simulation. I only just need to know the value of the energy compared to some limit I can judge stability. If I have to do the simulation, why do I still use the direct method? Because when I simulate the trajectory, I already know its stability. So that becomes some tricky part. So finally, people figure out, okay, so this method, although it's not accurate, but maybe I can make some assumption. I can assume the sum of the two angles will increase as a simple function of the difference of two angles. So basically, like if there's many generator, all the generator will change in the same pattern, such as if I calculate the difference of any two generators, and I multiply by a simple factor, I can easily estimate the sum of those two generators. That assumption is very strong, but that can make this last atom be computable, right? Without doing simulation. Okay, so this entity is a trajectory dependent. I really need to know the trajectory. So that's why this entity function is not Lyapunov function. Lyapunov function doesn't depend on trajectory, but this entity function, first three item has very clear meaning of either potential or kinetic energy, but last item really depend on the trajectory. So it's like a dissipated energy. Without knowing the accurate trajectory, I can never calculate this last item accurately. But there's some approximate method. For instance, I can assume that the sum of the angle, the change on the sum angle is linearly changed with the difference of the angle. Okay, by using to estimate this factor. The factor can use the value during the fault. I measure the angle. So if there's all the generators, I pick a two time point. So first is when the maybe before the fault happened, that steady equilibrium point. The next is when the fault is clear. I collect those values. Using those values, I can estimate K by this formula. Okay, then I can replace the differential of a sum of angle by simulate the differential of the difference angle. So this one will be changed to K d theta ij. So that will make the last item also be path independent. So that can become some type of energy. Okay, I can estimate the total energy. So that is introduced by this reference. If you have interest, you can take a look at that paper. So finally, I can summarize the procedure of transient energy function for multi-machine system. So first, you can run time domain simulation up to the instant of the fault clearing to obtain the angle, speed of all generator, and so that will be can calculate the energy when the fault is clear. Then you calculate the critical energy. Critical energy will be similar to the equal area criteria. You can find out the one unstable equilibrium point. You calculate that critical energy. So usually you can take either the unstable equilibrium point closer to the post-fault equilibrium, or maybe find someone is in the same direction. It's called controlling UEP. So if that difference is positive, which means the system will be stable. So let's go back to that original figure, which indicate the idea. That's a ball moving on the surface. Yeah, this one. Right. So this is SCP, and this could be another. It's a one UEP. But this one is on the path of the disturbance. So this one is more like a controlling UEP, so more relevant to the fault. But there could be another UEP which is closer, which have a shorter distance to the ICP. that is considered the closest UEP. Some methods suggest you use the closest UEP to give you a more conservative result. Some suggest you maybe to find the UEP in the direction. Okay, so if the initial energy is less than the critical energy, then the system will be stable. The critical energy can be estimated based on the controlling UEP or the closest UEP. Okay, so that's the end of the transient stability session. On Thursday, we'll start the voltage stability section.